grief minimized, vomit repressed. Understand? Please, Harrison,
I
go.
just had a question.
Yes.
I had a piece of paper attached to this. Is that somewhere in there, or?
Must be yours.
Thank you.
Somehow it got removed. What do you say? No, that's okay. I saw a motion.
I got a real quick question.
Will, please.
I think it's from a couple of quizzes ago.
Oh, go.
If our p-value for something occurring is less than 5%,
Yes.
is the opposite occurrence p-value just greater than 5%, or is it 95? Or yeah, help me out.
Okay, it's okay. And I want to make sure I understand when you say opposite. I want to make sure I understand what you mean by opposite. So,
caffeine does enhance lung function, or caffeine doesn't.
okay, now that's,
Something like that.
we have to be careful. The p-value you're testing, the p-value that you get as a result of your experiments, we're going to get like 5 or 6 of them today, if we can get to all the experiments I kind of have planned in here. When you get that p-value, it's the chance that you got your data, given that, assuming that your null hypothesis is true. Right? That's what that is. The opposite of that is that you should have gotten other data, assuming your null hypothesis is true. Nowhere in a p-value or its complement is the alternative hypothesis is true ever a part of it. That's why I wanted to make sure I understand when you say opposite, it has nothing to do with the null hypothesis being wrong.
Okay.
We haven't tested that yet. That's a type 2 error. That's a type 2 error. A p-value always assumes the null is right, and it checks for agreement of your data with that null hypothesis. So when you check your agreement, for example, caffeine, you said caffeine and
Lung function.
lung function. Okay, so you're trying to see if caffeine, let's just say you have a theory that caffeine increases lung function. Let's just make that, well, that would probably be predictable, wouldn't it? Let's say you predict that caffeine decreases lung function. That's probably less believable, because you think caffeine would be a stimulant, would jack everything up, including lung function. Maybe. Your null hypothesis would be no, caffeine does not increase lung function. It doesn't have any effect at all on lung function's increase. That's your null hypothesis. That's what you don't want to believe, what you go in stating and looking for a contradiction. P-value comes back, let's say it comes back at 3.2% or something like that. It's very small. And you go, wow, I wasn't expecting caffeine to decrease lung function, but my God, it seems to have, because the data I got does not agree with my null hypothesis. So that's a disagreement, there's your small p-value. The complement of that, if you say less than 5%, will be greater than 5%. And the reason it's greater than 5% is, if that's the data you got, the chance you should have gotten other data would have been whatever's left over. If hopefully that makes sense. So yeah, the trick with opposite is there's the opposite of the data that you got, and there's the opposite of a hypothesis you're testing. The p-value only deals with the opposite of the data that you got with respect to the null hypothesis. Hopefully that answer didn't make it even worse.
Yeah.
It may have. It's tricky because of that 2x2 contingency table.
Right.
2 ways to be right, 2 ways to be wrong, and the p-value only addresses one row of that table, so to speak. If you look back to that false positive, false negative, it only looks at the false positive row, which is the one where the null hypothesis is right versus missing it. Is that fair?
Yeah.
Okay.
Yeah.
And I think the more we get into these, the more we're going to catch that. And this brings up a good point too. Make sure if you think you got docked points on the quiz that you shouldn't have, just come see me. I caught a couple yesterday, and it wasn't anybody's fault. It was a miscommunication on my part to Emily, who grades your quizzes, that somebody had made a mistake up high and continued to use the wrong number for the entire quiz, and they got docked for every single problem, even though they were doing the correct math and analysis on wrong numbers. I never, if you get something wrong originally, I'll knock you points for that, and then if you keep doing the correct thing on wrong numbers, I'll give you, obviously, give you full credit because you're doing the right thing. So if that happened to you, thanks for bringing this up, Will. If that happened to you guys in quizzes, or if it happens in projects, I think Emily wants to do great projects too. Just let me know. Let me know and I can get back in there and fix those for you. Yeah? Ish? Okay, ish. Good. Anything in here? Hypothesis testing? Was the template okay to follow in the back? Hopefully. Hopefully. It's got more parts than the 4 steps that I talk about in class. And when I say 4 steps, I'm really kind of a lion dash. There's actually 5 steps. Because we finish, and then I ask what kind of error you could make. Like, at least conversationally. I asked you on the quiz for this week too. When you're going to test your, I think the quiz I uploaded this one is a test that you test to see, it's a little psychology test that was linked to the New York Times years and years and years ago, Johns Hopkins study, trying to see if you're observant enough to catch colors shown before you very, very quickly. And I like those. I like those because it's a way to get data from you guys right away, generate p-values, interpret the p-values, and see if you can be wrong. And we're going to keep doing that. We're going to keep looking at those as we go through. Anything, please? 100% fine. That's okay. That's good. That's good. And like I said, I'm going to keep linking videos and keep having stuff linked off the sites. Yeah, that's that. Okay. Now let me mute this. We don't need it right now. You need that video later. The quiz for Thursday, and the stuff we were talking about last week actually, it was pretty much all of last week, was the beginning of hypothesis testing. I'm just going to start that up here in a little flow chart. Hypothesis testing. And I'm going to make a flow chart for you guys in PowerPoint. I haven't gotten around to it yet, I apologize. And we're going to add to it every time we need to add to the manner in which we test things. So what we just got done was we asked ourselves a question, okay, what kind of data do we have? What kind of data do we have? Start by asking yourself that question. And there's a bunch of different kinds of data you can have. You can have qualitative data. You can have qualitative data. This often happens. Qualitative. I was back east playing shows this past weekend, and my bass player, who's a history major, asked me to do some statistics for him. In particular, being able to run some trend changes on some data. He's talking about he's doing his PhD right now on trafficking of human organs. Totally awesome sounding thing, actually. He gave me some of the source, so I'm like, that is completely freaking morbid and really, really interesting. And he's like, can you run some numbers for me? I'm like, sure. What are you talking about? He's like, well, I got body types, I've got this, I've got arms and legs and blah, blah, blah. I'm like, I can't do anything with that. He's like, well, what do you mean? He's like, I'm like, you're looking to check trends and measure them using p-values. He's like, yeah. I'm like, that's qualitative data. What kind of data do you have to have in order to do any of the stuff we're talking about? It's got to be numbers. You have to have numbers. I mean, the whole point of these curves we're drawing is that those curves have a numerical scale on them. If you move the numbers around on the scale, they don't make sense anymore. If you take arms and legs and twitch them like this on a bar graph, that's just a different bar graph. It's still valid. But if you take 1 and 0 and move it like this, buildings start falling down. Your clothes fall off your body because the sewing didn't happen right. I mean, dogs and cats living together mass hysteria, to quote Ghostbusters. So really, if you have qualitative data, you can't do anything with it as far as hypothesis testing goes. You're done. You're done. The best thing you can do is summarize it in some kind of a plot. You put a pie chart together, put it out there. I'm not saying that's useless. I'm saying that's actually good. You can look for changes from time period to time period to time period, but it's not what you can do with it. So then you have quantitative data. Then you have quantitative data. We like this. We can actually do stuff with this. We can actually do stuff with this. And so far, there's 2 types of quantitative data that we have. And thinking back to 243, what are those 2 types? What are those 2 types? Looking back to 243. And this is going back a ways. I mean, we've addressed both of them already in this class with confidence intervals. Discrete and continuous. Absolutely fine, thank you. We've got discrete. And we've got continuous. Yes. Continuous. Now, if you further analyze the type of data that you have, because you can have discrete data, and discrete data can take on many, many forms. What was the type of discrete data we spent a lot of time in 243 playing with? And I'm pretty sure Donna did the exact same thing. I'm fairly sure she spent the most time on one particular discrete distribution in 243. And that was which one? Actually, it becomes the bell shape as the sample size gets larger, but the bell shape is actually continuous data for the most part. Thank you. Thank you, Michael. Say it again?
Binomial?
The binomial was the one, Harrison, yeah. Now, they do link to each other, Michael. I'm not trying to say it's not bell-shaped. For certain values of p and or large enough sample sizes, they become one another. But generally, you've got choices. You've got the binomial. You also have others. You've got other ones. I'm not going to list them all out. I'll just number them 1, 2, 3. I will put one more. I'll put multinomial down here. Multinomial, which is related to binomial, except instead of having 2 outcomes that are mutually exclusive, you can have as many as you want. So that's the difference between multinomial and binomial. Binomial is a subset. There's also geometric, hypergeometric, Poisson. There's all kinds of distributions in there. They're all wonderful. They're all wonderful. The trick is Gesundheit. There are tests for all of these things. There are tests for all of these distributions, but I'm going to choose, if that's okay with you guys, to ignore most of them. We'll get to this kind towards the end of class. That's what we need a goodness of fit test for. We'll get into him later. But this guy right here, this is what we just got done talking about with the one prop Z test that we were running last week. And that you'll run on Thursday for your quiz. Well, hopefully not Thursday, you'll run on Wednesday at some point today, before Thursday. Now, the reason I show you this flow chart is because I want you to realize how much goes into the process of inferential stat before you grab your technology and start crunching numbers. You have to decide that's what you want to do. Go get your data. Identify your data. It has to filter through all of this to get to this. So it's why it's a little bit fictitious in this class when I hand you a data list with 4 pages of data on it. Here's your data. Boom, go. It's a little bit fictitious. Getting the data is 99.994% of the struggle. And it's got to be of a very, very specific type. So, okay. So that's discrete. Multinomial, like I said, we'll deal with that in goodness of fit testing. There are other types. There are other things you can do. I'm going to have you analyze a few as we go in the out-of-class exams as the term goes on. But that's pretty much the only kind of discrete data I want to play with in this class. Now do me a favor. Grab that data list of yours. Grab that data list of yours. This is 243. I need that. I need my data list, which is put down somewhere. You guys. Amber. Emily. Oh, it's here. Rachel, you don't have one of these, do you? You don't. Here you go. Go. And take a look down low. We've gone through those first 3 data sets. Those are all discrete. They're all like, oh, Justine, you do too. Stable for you. There you go. Take a look at the first one that's labeled single mean testing. Single mean testing. For a sec.